The first slide in front of us here, we are discussing why do we need the applied element method in doing a structural analysis. Um, so the structure behavior for any kind of material like reinforced the concrete material or steel material or brick material, it goes through phases through its behavior, starting from the quantum phase and the discrete phase. The quantum phase, the the structure is first uh, being in the linear stage where everything behave like in a linear way, and then when more loads are added on the structure, it goes to cracking, yielding, and sometimes you can see the crushing. Also, for the steel reinforcement or even the steel members, you see buckling and the post buckling. And then you move to the discrete behavior of the material, where elements start to separate from each other, leading to debris falling as rigid bodies, and these debris collide together or collide with the ground. This is like the natural behavior of any structure when it's built, and then it goes to the death where there is an extreme event happen on the building. So engineers, they are used on the FEM, the finite element method. It's very good when it comes to linear analysis, especially if you want to reduce some nonlinearities in your model using FEM, especially if you are using the simplified nonlinear analysis, you have to put some assumptions in your model. For example, the locations of the plastic hinges. Where are the location of the plastic hinges? And note that the structure is only going to behave non-linearly only at the locations that you are going to assign these plastic hinges to. Uh, One of the other assumptions is including the p delta effect. Either you include it in an approximate way or an accurate way. Of course, when you're adding it as an accurate way, it increases the running time of your analysis. One of the other assumptions is the rigidity of the connection, like the end offsets that you have to put in your model if you're doing a element analysis. And then when it comes to element separation and debris and collision, finite element methods, especially the simplified methods, it cannot be used to have element separation or debris or the collision. However, you can still have these element separation and the discrete behavior if you are using something like LS-DYNA or ANSYS or Abacus. However, they use the methodology of what's called element erosion technique, where they remove the element when it reaches to a certain strain, and then the removed element, its mass is actually added on the neighborhood elements beside it, leading to more masses added on the structure. So somehow the behavior is not very realistic. Another way of doing analysis is to do it using the DEM, the discrete element method. The discrete the discrete element method, it has some problems when you are doing static analysis and especially like steel members and buckling and so on. So it has problems in simulating the quantum behavior of the material. However, it's very good when it comes to element separation and debris and the collision. That's why we have now the applied element method, which is you can consider it as a combination from the FEM and the DM method, where it covers the whole structure behavior starting from the linear stage, going to cracking, yielding, buckling, element separation, debris, and collision. And all of these are done automated inside the technology that we are using. Let me give you an example in here. So we have modeled the Champlain Tower that collapsed in Miami, Florida, like 2 years ago. And in here, we just assumed that two columns from the bottom floor has been removed from the analysis, leading to the progressive collapse of the building. So we see here the middle part of the building collapsing, followed by the part here on the right hand side. This is just an assumption, so we don't really know what happened in this case. We just assumed the two columns from the bottom floor has been removed, and we see the analysis in front of us. the the runtime for this analysis, it took around 8 hours on a regular computer. So the running time of ELS is much more faster than if you are using FEM analysis doing a collapse analysis. And the advantages of the technology is that it gives you an inside details of the behavior of the structure, like where the elements are going to be separated, where the reinforcement rebars are yielding. Are the reinforcement rebar reloading or unloading and reloading, and then they reach to its ultimate stress and fail, or it just like uh, keep loading and unloading, and everything is in a stable position. So the behavior or the structure or the ELS gives you an inside detail on the actual behavior of the structure when there is an extreme event happen on it. Let us see here this footage from a camera where we see here exactly what we have seen in the simulation. The middle part of the building collapsed, followed by the part here on the right hand side. Comparing also in on the level of the debris, like we took a screenshot from the debris that they offered online, and we see here the structural drawing of the building. This is the actual debris field, and this is the debris field that obtained from the ELS. Let's see, for example, this shear wall in here. So this shear wall in here located at the part that failed last. So we see that this shear wall, when it failed, it went all the way to this area. And we can see it in here. So it went all the way to this area. And this is very similar to what we got here from ELS. The other shear wall that we have seen in the uncollapsed part was intact and no failure happened in it. And we see it here also with no failure happening. We see also the pancake collapse of this part in here, and it is very close to what we got in here. Now, let's see formation inside FEM analysis. So we have an example in here for a 2D frame. It's a reinforced concrete frame, and they removed a column from the first floor here, and then they did like a push down analysis on the connection in here. We see here the curtailment of the reinforcement at the first and the second floor, and this figure is showing here the curtailment of the reinforcement and the geometry of the last floor in here. Now, if you are using FEM analysis, the simplified FEM analysis, where you have to assign plastic hinge locations, sometimes engineers has to assume the locations of the plastic hinge as a figure A, while others they will assume it as the figure B. Others are going to be more smart and they are going to put the plastic hinge location at every change where they have a change in the reinforcement details. And others are going just to divide every frame element into several elements and then assign plastic hinge locations at each one of them. So this means from this chart that or this figure that the plastic hinge assumption, it's an input, not an output. So let's see here the analysis of the ELS, or let us have a chance first to see how the structure behaved when they removed the column from here. So as soon as the column was removed, we see here an initiation of the cracking near the curtailment, or where we have curtailment of the reinforcement. And this happened only in the first floor and the second floor. However, in the third floor, we see here that the cracking happened near the connection in here. So this means that the plastic hinge can happen anywhere inside your building, even in the columns. It can happen anywhere when you are doing an actual case of a progressive collapse analysis. Now, let's see the analysis of the ELS and how the ELS was able to predict the locations of the plastic hinges and the cracking that happened. So we did the same example by modeling the reinforcement three bars, the same geometry, same loads, same everything. We just ran the analysis and we see here from the analysis, this is the bending moment. And we see here the location of the cracking. The first crack happened here near the location of the curtailment of the reinforcement. And here on the top floor, we see that the cracking is happening near the connection in here. So this gives us an insight about how accurate is ELS in determining the cracking, propagation, and the separation of the elements up to the collapse level. And this also gives us an idea about how important is that the plastic hinge be an output instead of being an input, as you see in the frame element analysis. Now, let's have a look also on the comparison between the load and the deformation. So we got here we matched very well the initial stiffness, the yielding load, the cutting of the reinforcement rebars at different locations, followed by the catenary action, and then the total failure. This is a comparison between the final stage of the frame versus ELS, and we see that they are in a very good agreement with each other. Now, let us speak about the applied element method itself. What is the applied element method? The applied element method, it is a stiffness-based method similar to FEM, where we discretize the structure component into several solid elements, and then we connect those elements together with what we call material springs. The material springs represents the axial deformations as well as the shear deformations happens inside the material. As an example, we have here a reinforced concrete column. And as we can see here, we are discretizing the column into elements, as we can see in here. And in the first or in the beginning, let's speak about um, the concrete material and how we generate the connectivity between the elements. So we are highlighting here on those two elements, element number one and element number two. And what happened inside in ELS is that we generate a group of springs between each two elements. Basically, they are a 5 by 5 springs, which is a 25 springs that are generated between each two elements. And this is for the concrete material alone. Each of those 25 springs is actually three kinds of springs. One normal spring for the normal deformation, and two shear springs for the shear deformations, one in XZ direction and one in YZ direction. We are speaking about the reinforcement rebars inside the column. So let's assume that we have a reinforcement rebar that's going to pass between those two elements. In this case, it's going to be a stirrup. So we replace the reinforcement rebar at its exact location inside the element with, again, one normal spring for the normal deformations and two shear springs for the shear deformations. This way of modeling reinforcement rebar doesn't take into account the debonding and the slippage of the reinforcement rebar from the element around it because it is just a spring. However, if the user want to simulate the behavior of the debonding and the slippage of the reinforcement rebar, he can simply modify this reinforcement rebar to be a solid element. And then he would have to define an interface material between the reinforcement rebar as an element and the concrete around it as an element. There are some differences between the applied element method and the finite element method. For example, the first one is that when we apply here a tension load or on a member like this in the FEM, we see that the elements deforms. However, the nodes cannot be separated from each other. Here, in the applied element method, the element itself is rigid. No deformations is happening inside the elements. All the deformations are happening at the interfaces between the elements where the springs are located. So if we are applying here a tension displacement of 1 inch, a total displacement of 1 inch, you will find here that the total displacement is 1 inch. Here also is going to be 1 inch, same as FEM. Another difference is in the number of the degrees of the freedom. If you are using LS Dyna or ANSYS and you are using a brick element, basically an element with an 8 node, then you have 3 degrees of the freedom for each node, leading to 24 degrees of the freedom for each element. Here, because we don't have nodes, we have the degrees of the freedom in the CG of the elements. And this leads to 6 degrees of the freedom, 3 for the translation, and 3 for the rotation. And this actually makes the solver of the applied element method much more faster than FEM if you are using a solid element in your analysis. One of the differences also is in the connectivity between the elements. Here, if you have an example like this, like two members overlapping at a surface like this is a problem in the finite element method because you have to have nodal compatibility. In the applied element method, this is not a problem. Any element that overlaps with another element or share it in its face, springs and connectivity are going to be generated automatically. And this actually makes the meshing inside the applied element method much more efficient than the finite element method. So in case of the finite element, if you have an area of a coarse mesh and area of a fine mesh, in FEM you have to have a transition zone between them. However, in the applied element method, theoretically, you don't need to have a transition zone between them. Between each big element and small elements, 25 springs are going to be generated in here. And of course, the user have full control over the kind of springs or the kind of material that can be generated between two interfaces. All our material models that we use are nonlinear material models. For example, this is the material model that we use for the concrete, and this is the material model that we use for the steel. And recently, we have developed the capability for the users to define their own material model, and this is called the user-defined material model. And we introduced in this model a lot of capabilities, like, for example, including the fracture energy in your analysis, either for the concrete or for the steel or for the brick or for the mortar. Also, the strain rate effect is automated inside the user-defined material model. The confinement effect is also automated. All of these are automated inside the user-defined material model. Finally, this is what you get if you are doing FEM analysis for a case where the structure will collapse, where everything more like behave like a rubber. However, this is what you get from ELS here if you are doing a collapse case and you want to see debris falling on the ground. Let me stop here and ask if anyone has a question about the applied element method.
Good afternoon. Can you hear me?
Yes, I can hear you.
Okay, perfect. Thank you for this beginning of the presentation. Very interesting. I have a question about the spring, if I can.
Okay, sure.
Okay, yeah. If I understood correctly, the number of the springs in each, let's say, border surface between two sub-elements is 25. Is it correct?
Yeah, yeah.
Okay, and my curiosity is about how are they distributed? I mean, this 25 is it a fixed number, or is it possible to play in a sense with this number? How does it
Yes.
work?
So by default, it is a 5 by 5 springs between each two elements. However, there is a capability inside the technology to allow some regions in the structure to have more than a 5 by 5. You can make it like 9 by 9, 10 by 10, whatever number you want to do. And
Okay.
the way we distribute the springs. So for example, in a case like this, when you have a big element in here and beside it a small element, so between each big element and every small element there will be a 5 by 5 springs that are generated.
Okay. Very clear. Thank you. Thank you so much.
You're welcome.
I have a question too.
Sure.
Can you hear me?
Yeah.
Yeah. So first of all, thanks for the presentation. And my question is related to the sensitivity to the mesh size. So, I mean, you just showed about two meshes or one mesh with two size of elements. And my question is, does the size of the element interact or is influenced by the stiffness of the springs or vice versa? Is
Definitely, yeah.
the stiffness of the springs influenced by the size of the elements, and how do you cope with that?
Yes. So the applied element method is same as FEM if you're doing a solid analysis, like or a solid modeling analysis. You have to make a mesh sensitivity to be able to have a conversion for your analysis. So it is exactly same as FEM.
Okay, thank you very much.
You're welcome.
Sorry, can I also have a question?
Sure.
Yeah, thank you very much for the presentation. My question is still related with the mass sensitivity. As we are aware in finite element, for example, there is a certain material behavior. For example, when you have a softening in concrete, for example, you need to adjust the level of strain to displacement to avoid the the influence of the mass sensitivity. Do
Yeah.
we also need to do the same in applied element method to to reduce the sensitivity to the softening behavior?
Yes, definitely. And this is what we mean by the fracture energy. When we included the fracture energy, it is very much related to the element size of your model. So we always advise the user to include the fracture energy in their analysis to account for the size of the element.
Okay, okay, that's very clear. Thank you very much.
You're welcome. All right, so we will continue the presentation. Um, so let's speak about the technology now. So the technology is divided into three parts. The first part is the ELS modeler, where you can model columns, beams, slabs, brick walls with its mortar, uh, pre-stressing beams, slabs, whatever, or most of the basic components that you see in the construction material, you will be able to see a component for it inside ELS. And then you apply the materials and the boundary conditions and the loading, and then we send the data to the solver to do the analysis. And then we can see here in the viewer the results of our analysis. Either it is deformity shape, either it is eigenmodes, if you wish to see the eigenmodes of your analysis, internal force diagrams like bending moments, shear, normal, every internal force you will be able to see it inside ELS, plus the ability to see the stresses and the strains in each spring inside your model. So there are many output options that we have here inside ELS, and while we are going through the presentation, we will be able to show you some of the examples that we have in here. Now, for every numerical analysis method, there must be some verification examples. I have chosen here some verification examples for many applications. So I'm going to start with this one. We have here a steel, a concentric braced frame under a cyclic loading. and this is the experiment that was done in the lab. And this is the ELS model that we created for this case, where we took into consideration all the detailing that you see in the lab, and then we applied the cyclic loading on the frame. And let's see together here. Let's first here see the output results. This is a direct output from ELS, so this is not like a video editing tool. This is direct output from ELS, where we can see here a global buckling happening in the bracing, and we can see here the degradation of the stiffness. We also see here local buckling happening in the flanges of the column near the connection. And let's compare this to what we see from the analysis or from the experiment. So we see here the local buckling that's happening in the flanges. We see here cracking that happened in the gusset plate here. And we see here the fracture that happened in the bracing that we have in here. Now, comparing between the load and the deformations, we see here that the failure happened at around 230 kips, and this is what we got here from ELS. The failure also was around 230 kips. Another example that we have here, or let me show you another example also for a seismic analysis, since we are here already in the seismic, which is basically there are some buildings in the Krogenian region in Netherlands, and these are made from unreinforced masonry walls. And what we have in here is a series of verification examples for ELS in the cyclic loading, either in plane or out of the plane for the clay bricks or the calcium silicate bricks. So let's see the first example in here. We have a wall. It's made of clay, and these are the cycles that was applied on it up to the failure. So we see here from the analysis, very good agreement between the hysteresis. And we see also very good agreement with the cracking that's obtained from the experiment versus ELS. Another, or let's see here the mechanism of the failure. So because this wall is a cylinder wall, so we are expecting here that the behavior is going to be more like rocking. And this is what we see from the analysis in here. Another example for a squat wall, also this is a clay material. And this is a comparison between the ELS results and the lab hysteresis. And this is a comparison between the cracking obtained from the experiment versus the cracking that was obtained from ELS. Also, we are showing here this video showing the shear cracking. Up to the failure. And then there is also here the out of the plane behavior for the clay walls. So they have the wall now on a shaking table test, and they applied a series of earthquakes on it. And we see here a comparison between the ELS results in terms of hysteresis and in terms of the cracking. And let's see a video showing what happened. Up to the failure, as we can see in here. Another another type of the brick, it's the calcium silicate bricks. Also, this is the squat wall, and this is a comparison between the cracking obtained from ELS versus the cracking obtained from the lab, and this is a comparison between the hysteresis for both of them. Another example for the out of the plane behavior for the calcium silicate walls as well, and we see here the cracking obtained from ELS versus the cracking that was obtained from the lab. Also, there are some kind of walls that's called cavity walls, where there are two leaves from the walls, and they are connected together using ties. The ELS was able also to make an out-of-plane behavior for this case, and this is a comparison between the cracking obtained here and here for each leaf of the wall, and the hysteresis that was obtained from the lab versus the hysteresis obtained from ELS. So along the the presentation and with every application, we are going to show some verification examples. Now, let's go and have a quick look on the ELS capabilities in the modeling. So I prefer to make this through an example or to open ELS in front of you and show you how easy is modeling inside ELS. Let's open ELS together and see how easy is modeling inside and how we made it very convenient for the user to do modeling as fast as he can so that he doesn't spend so much time in modeling and still get very accurate results from the analysis. The first screen in here appear, it asks you about the first level height. Let's assume that the first level height is 150 inches, and I'm going to press OK. This will open up the main modeling window of ELS, where we have here some icons. Here mainly are some toolbars for the drafting layers as any other CAD, like draw a line, draw a circle, draw a rectangle, whatever object, you can draw it from here. And then we have here a toolbar for the modeling of the components, like a column, a circular column, a beam, a slab, reinforcement rebars, brick walls, window glazing, and then the steel members that we see, either it is a column or a beam. Now, let's, for example, model a column. How do we model a reinforced concrete column? You can model it in the 2D view or in the 3D view. The good thing here about ELS is that there are predefined styles inside ELS, and I'm going to explain what is a style. A style, for example, for a column, it is the geometry of the column, the main material of the column, plus the reinforcement rebars inside it, plus if you have a combination of a geometry like a concrete material plus reinforcement rebars plus a steel member that might be embedded inside it, all of these, this is a combination of a style for a column. If, for example, I need to model an RC column, I would just go here to the steel section and choose none. And now I'm going to define the geometry of the column plus the reinforcement rebars inside. So for the column, you can here assign the width and the depth of the column. Let's put here some numbers, as well as the material of it. Either it is a normal concrete material or any of the predefined materials that we have in the library. Click on apply, and then you can open here the reinforcement rebars, where you can see here the basic uh, uh, needed information to model a column, like the cover. You can assign the cover for the reinforcement rebars, the number of rebars in each direction, direction 2 or direction 3. So for example, if I need to put 3 bars at each direction, so I will put here 3 and choose the area of the rebar. And then in the other direction, I need to put also 3. But I need to exclude the corner rebars because these are included in direction 2. So this means I only need one rebar to be added in here, and also choose the area of it and the material for these rebars. Then you assign the number of the branches of the stirrups in each direction, and then the spacing in between the stirrups and the area of the stirrups. Click apply, and then OK and OK. Now I have the first style modeled, or it is ready. To be able to model it, as we said, you can do it in the 3D mode or in the 2D mode. I'll just click on the column here, and we can insert the column anywhere. We are not governed by the grids. For example, you can model any column, any beam, any slab, anywhere inside your model without the need of actually having a grid to be able to do so. So we see here the reinforcement rebars that's inside the columns, and we see the geometry of the column. The ELS comes with a default mesh that you can change. Maybe it's better to view this as solid elements and shrink those elements just to be able to see them. And here you can define the height of the column. By default, it is the same level height that we have assigned from the beginning. And you can see here the height, and then you can change the meshing to whatever number you want. So I just throw here a number, 30 elements along the height, 3 by 3 along the width and the depth of the member. So now we are modeling the column as the springs or as reinforcement rebars are going to be generated as the springs. How about if we want to model the slippage behavior and the debonding behavior between them? So it is easy as if you go here to the additional task menu and then go to reinforcement, and you convert this reinforcement into a mesh. Now let's go ahead and hide the column. You will be able to see the mesh as solid elements that has been created inside ELS, and it takes into consideration the cover measured exactly as you have done. It's also taking into consideration the hooks if you have hooks, and these are all automated inside. All what I have to do now is to intersect the elements of the column with the elements of the reinforcement rebars inside it. And this can be done here by checking the integrity. So the ELS will tell you that you have here integrity problems or intersections problems, and you just need to swap this so that the steel members, which are represented as 8 nodes, be intersecting the column itself. And the ELS will do the cutting by itself, and you have now a column made of reinforced concrete as well as reinforcement rebars inside it, modeled as a solid element. I will just go back to the main configuration where we have here the springs, and let's see how about if we model a girder. I will just take a copy from this column in here, and then I'm going to specify the distance between both columns. Let's assume that it is 200 inches, and we have here a copy from the column in here. How about if we need to change the dimensions of the column in here? I have here another style. It has bigger geometry. It has other reinforcement rebars inside it. All what I have to do is to select this column, and from the properties, I will make it column style number 2. And we see here an update in the geometry as well as the reinforcement rebars. How about if I need to model this big column from the beginning? You can go here from the styles, set this one as the default style, and now if we pick here, it's going to be the default that we are going to insert in the modeling window. Let's have a look here on the girders, more like it is the same as the column. You can here assign the geometry, and you can assign the reinforcement rebars inside and just model it as from the face of the column here, from the mid location, and I'm using the snapping options in here to be able to go here and model the girder. By default, we have an extension for the reinforcement rebars of the beams inside any object beside it. So you have here an extension for the reinforcement rebars. And this extension can be modified here from the properties. If you need to change it to be any other value, it will be changed here automatically. How about if we want to model a brick wall? Let me just go ahead and do some meshing on this girder. And let's display it also as a solid and shrink. Let's go ahead and go to the styles, go to the walls, and in the walls here, we can choose here the thickness of the wall. Let's assume it is 6-inch wall. And here you put the dimensions of the brick, length, height, and width. And also you define the mortar material that's going to be generated in between them. So I will just keep it as default as mortar. And I'm going to model it from, again, the mid location of the column to the mid location of the other column in here. And we can show this one again as solid and shrink. We can see here an intersection between the, the, the masonry wall and the beam. All what I have to do is to reduce the height of this wall to account for the beam dimensions, as you can see in here. How about if we want to include an opening inside this wall? Just go here to add opening, and the opening is created. Even we cut the brick exactly as you can see, like in any actual construction, we cut the brick as you can see it at any wall you see it. Can also control the size of this opening from here, as well as the location of this opening inside the wall. Can move it up or down or anywhere inside your model. Now, let's go ahead and do a slab. I will just take a copy. We can exclude the wall for now from our copy. And I can choose now to do an array instead of a copy. 2 copies at a distance of 200 inches. And OK. So we have here an exact copy. And then you can also close this by adding here another beam. We can take a copy from this beam from here to here. Now let's model a slab. Slab style number 1. Same exact concept. I need the thickness. Let's assume it is 5-inch with a material of a concrete. And then you assign the reinforcement rebars. I will just make it something easy, like 12 inches in each direction, top and bottom, with an area of number, let's choose number 4, for example. By the way, speaking about the reinforcement in here and the fixed numbers that we have, you can change these numbers or add to it anytime. So if you go to tools here, rebars. This is the default rebars that we have, and these areas are according to the US code, of course. You can have rebars, bolts, and the screws also. If you need to add more areas, you can just add it as user defined, and you can even name it anything. And whenever you go to any of the styles in here, if you go to the properties of one of the styles, you will be able to see the new added reinforcement rebar in here. Let's do some meshing in this beam, and then we can add the slab into our analysis. By the way, we can also control here the view to be solid or wireframe from these two buttons, and it goes or it applies on the whole model. Now let's go ahead and model the slab. I like to model it in the 2D view because it gives me control over the corners that I want to snap to. And we have it here modeled. Let me save a copy from the file. And let's go ahead and define some meshing again for the slab. Let's choose, for example, 30 by 30 by 1. And we have this now modeled. How about if we need to add extra reinforcement inside the slab or inside the beam or inside the column or even the walls in here? Modeling reinforcement rebars in ELS is as easy as drawing a line with any shape and converting it to a reinforcement rebar. So for example, I can draw some lines like this. Assume that you have a rebar that looks like this. And let's also make some or take some copies from it. And it is as easy as selecting all these lines, and from the additional task menu, convert to draft to general reinforcement rebars. It will ask you about the area, the material, and even if you have a pre-stressing force inside them, you can add them in here. Now I have finished the conversion. I just need to move it to the place I'm going to add the reinforcement rebars to. For example, here, and then we can drop it down or make shift with the cover value -1 inch, and now it's going to be generated inside the model. Okay, let's do something here quickly. I'm just going to assign a blast load on this building in here, and we see and we will see the behavior, how it looks like. Now let's begin by first define the materials. Let's have a look on the materials in here. In the materials, you can define here the Young's modulus, the shear modulus, the specific weight of the material to account for the mass, the compressive strength and the tensile strength of the material, as well as the shear strength of the material. And here, if you click on plot the stress and strain, you will find the backbone curve of your material model. Same thing for the reinforcement rebars or the normal steel. You can assign here the Young's modulus, the shear modulus of the material, as well as the yield strength of the material and the ultimate strength as factor from the yield. Let's put it like 1.3, for example, and then apply. And also you will see here the backbone curve of your material. If you want to speak about also, if you want to define a user-defined material model just as an example, I can take one of the concrete models, convert it to user-defined material model, and here we give the user more options in his design or in his materials. For example, the failure and the residual. Do you want the failure to be more column with the fracture energy included, or the more column with gradual softening? Or if this is a steel model, for example, you can use von Mises with also either gradual softening after the spring reaches to its ultimate stress, or basically a modified fracture energy. Moreover, if you have something like screws or bolts and you need it to fail at a certain stress limit, this actually gives the user the ability to make the material feel as either on the normal, like in tension alone, or in the shear alone. This is also applied here in the stress limit. For also including the effects like the strain rate effect. If we are talking here about defining an effect as the strain rate effect on the concrete material, for example, all what I have to do is to go here, add effect. You have the effect here of the strain rate, temperature. If you are doing a analysis on temperature, like heating of the concrete or the cooling of the concrete, the time based as the creep, for example, or the confinement effect, where it's also here. If you go, for example, to the strain rate effect, and we generate curves here automatically, so that when you start the strain at a certain value and end the strain and this value, I can ask ELS to give me like a 10 curves or 100 curves, so that it covers the whole history of the strains that I have during the dynamic effect. So all of these are included in the user-defined material model. Let's have a look here quickly on the loading. The first stage of loading, it's always a static stage to account for the dead loads, live loads, and so on. And then you can add either more static stages or more dynamic stages. For the static stages, you can add here either concentrated loads, displacement, hydrostatic pressure, uniform pressure, moving loads, line loads, and also you have the ability to add what we call static open foam load. If you are doing your wind analysis on open foam, the CFD solver open foam, you can import these pressures directly inside ELS as a steady state pressure. And this is a feature that is available inside ELS. Speaking about the dynamic analysis, you can also have here concentrated loads as an impact, displacement, earthquake as a acceleration in X, Y, and Z direction, blast loads, uniform pressure, moving load again, and finally, we have here what's called open foam. This is again a feature for the engineers who are using open foam or the CFD tools to do the blast analysis. It gives them more accurate pressure, and you can import it directly inside ELS in here. For now, I'm going to do a blast analysis using the conventional blast analysis. I'm going to use a very small time step for my analysis, and then I'm going to define now the load. Let's assume that the bump weight is 0.1 kip, and it is located at the center of this building. I'm just going to select here the center of the slab, and then I'm going to reduce the height of the bump to be exactly in the middle of the slab. When you click here on check, the ELS will be able to give you the arrival time, the duration, the pressure, the reflected the pressure, the impulse, and all the information that you need. And the ELS is going to apply the pressure based on the location of the bomb versus the angle of incidence between the location of the bomb and the element, as well as the standoff distance. So both of them are included so that ELS can calculate the pressure on each one of them. One final thing I want to do before running the analysis is to go to the output steps, and I want to see my output at every time step so that I can see more output and see more accurate behavior for the simulation. Now, let's go ahead and run the analysis. So the solver now started. We are applying now the on weights, and then we go to stage 2 where we applying the blast load. Now, we don't have to wait until the analysis is done to be able to view the results of the finished steps. We can now go to open the viewer. So we see here the viewer. When I click on the play command, we see here that the blast has reached to the wall as well as the slab in here. One of the good features that we can show here is that we can just hide the ground for now, and I want to see the pressure distribution on the building. So I'm just going to flip it just like this because it is an internal blast, and I'm going to go to blast pressure settings, and then I'm going to calculate the limits of my blast load. And now I can play the results and see the distribution of the blast. We can play it as a frame by frame to be able to capture it. So each element that the bomb source is seeing will have a pressure that is applied on it. We can update the results and see now the deformations happening. Now, let's go ahead and see the cracking in the building. This can be done by many ways. The first way is by viewing the principal strain contours, strain principal. Let's choose it for the current frame and apply. We can see here the distribution of the cracking on the building. By the way, by default, any masonry wall that is constructed inside ELS, the default material interface between any object and this wall is going to be a mortar material. That's why we are seeing here cracking happening at the interfaces between the wall and the column beside it. Another way for viewing the cracking is to plot what we call or see what we call spring status. The spring status allows you to show, for example, where are the springs that are separated, or where are the springs that are still in the elastic stage, where are the reinforcement rebars that yielded. which springs are in the tension, which springs are in the compression, which one are in the tensile failure, and so on. So whenever I activate this option and just go here, let's go to the tensile failure and view a wireframe mode, we can see here that all the springs in the wall and the building has reached to its ultimate strain and the stresses, of course. Perhaps if we go here, hide the tensile failure and show the yielded reinforcement bars. So all these lines that we see are location of reinforcement tree bars that has yielded. I can select, for example, one of these reinforcement tree bars. Let's select, for example, this one. And I can plot a relation between the spring strain versus the stresses. We see here that it is reaches to, let me update here, maybe, yeah. So it yielded, and then it is loading and unloading. So it did not fail yet. Let us also go and choose, for example, um, let's hide now the spring states and go and see the internal forces. So for example, I can go to those beams and I can go here to the internal forces and show here, for example, the moment. And we see here an animated bending moment diagram. We see here an uplift happening. You can also view the envelope if you would like. View envelope. We can hide the text of the original. Update. And we can view the bending moment vibrating in between the envelope. How about if we want to plot charts for displacements, for example? You can go ahead, select one element from the slab in here, and we can plot here a relation between the time versus the element displacement in z direction. So we see here that it is increasing and keep increasing because of the failure that's happening in here. How about if we take this to another level and let's go ahead and remove this column while the analysis is running. So we are now updating the solver with a removal of a member while the solver is running. Let's go here to remove elements, add action, add time action. At the time 0, this means to remove it instantaneously. If you have like a certain time that you want to remove it, you can. Now click OK. We see here that the solver says deactivate the elements that we have chosen. And now if we update the results, we will be able to see the behavior of the structure with the blast load, and then this column is removed. We can measure here the displacement of this element in the z direction and see here when we update, it should be going down at a certain time. we can go ahead also to make the analysis like more fa faster. We can change the time step of the analysis because the blast wave has already gone. So I can change the time step of my analysis. Change time step, add action, add time action, add 0. This is the new time step that I'm going to use, and this is the new output step that I'm going to use, and click OK. You should now be able to see the results much faster. Any of the questions about the viewer? Is there like a certain output that you want to see that I did not cover in here? Okay, so I think we'll stop now for like this analysis, and we will start now going through the applications of the ELS. Uh, Let me go here, and I will just keep this one running in the background, just to continue our presentation. Yeah, speaking about the applications of the ELS, so the first one in here, we are going to speak in more details about the blast analysis. So there are several ways to generate blast loads inside ELS. The first way is through the UFC code 334002, and this is what I have shown in the example, where you can where we have programmed these charts inside ELS so that the user can just put the bump weight, the bump location, and then the ELS will automatically calculate the arrival time, the duration, and so on. As an example for this, we have modeled here the Oklahoma buildings that collapsed back in the 90s due to an explosion. And we see here a very good agreement between the ELS as well as the actual accident that happened. Another way is by importing the blast pressure. So if you have your own blast pressure, you can import it inside ELS as uniform pressure on elements, and the ELS will be able to do the calculations according to this. And this is the example for a blast load on a column, and in this case the reinforcement rebars has been modeled as elements to be able to capture the permanent deformations as well as the debris falling and the cover spalling. Another way, by importing a CFD analysis inside ELS, you are able to do a more advanced blast analysis using ELS. As an example, we have here an example of a building that was solved on OpenFOAM, and then we were able to do the blast analysis on the building. We see here the reflections, and we see here the side the pressure going all the way inside the building. And we see here also the positive phase and the negative phase of the blast load. Of course, we don't need to assign any plastic hinge locations. The strain rate effect is automated in the user-defined material model, and we have seen also the internal forces diagrams and how they are generated. I will skip this example because of the time. Let's go here to another application, which is the progressive collapse analysis. Of course, we are using nonlinear structural analysis using nonlinear material models with automatic plastic hinge formation. The membrane action and the P delta effect are already included in the analysis. Plastic rotation calculations are already inside ELS, and the final thing is a debris loading. So if you are solving a case like a progressive collapse analysis on the third floor, and some debris has been generated from the floors above, so these debris impact on the floor below are considered in the analysis. We have here another example or another verification example for a case of a progressive collapse analysis with infill walls, where we have here the model, the ELS model, and we removed this column from the analysis. Let's here see the results of the ELS. We see here the failure that happened again at the location of the curtailment of the reinforcement, followed by failure here, and we see the cracking inside the masonry wall. This is a side by side for the actual cracking versus ELS. So we have here the failure or the fracture of the reinforcement rebars at this location, here and here, and also here. And these are similar to what we got here from ELS. This is a comparison between the ELS results and the experimental results. Another comparison also in the relation between the vertical movement of the joint here with the horizontal movement of the floors. And we see here at each floor they are matching very well. This is another example for a precast building. Um, and we see here failure happening near the connections. We see here the propagation of the cracking along the side of the slab and the punching shear failure at the back. In the next example in here, also this is a progressive collapse analysis, and we see here the effect of the membrane action on the behavior of the building. So this building, we didn't have any shear walls on the other direction of the wall. So we see here that the slab was strong enough that it pulled the building inward, leading to the collapse. We see here buckling and of the cold formed steel studs. Another application is a forensic engineering. So we have here the first example of a portal frame subjected to a lateral load. And we see here that there was like a deficiency in the anchors connecting the frame to the foundation. And we see here that uh, the anchor was removed from the foundation. Another example in here for the I-35 bridge. So this is an actual case that ASI was involved in, where we modeled this bridge that collapsed in Minnesota back in 2007. And this is the behavior of the bridge when it collapsed. We see here the sliding of the bearing. The same example again with different view. Another application is the seismic analysis. We have covered the verification example here before, so I'm just going to this example. This is the Pine Gold building that collapsed in New Zealand in 2011 due to an earthquake. And in here, we see the collapse shape of the building. In fact, this was granted from the European Commission that ASI has been awarded this grant for the first responders so that they have a fast running analysis tool to be able to predict the cavities inside the collapsed buildings so that if there are like the survivors inside, they can go ahead and use ELS to detect the cavities inside and use these cavities to get the survivors out. So we have here the ELS model for this case, where we modeled everything as we see in the structural drawings. And we see here the behavior of the building. The reason of the failure was a shear failure in the core of the building, as we can see in here. The Fraunhofer Institute of Technology in Germany, they did an LS Dyna model for the same building. And this is like a comparison between the real collapse versus ELS versus LS Dyna. It's good to note that ELS or the LS Dyna took 288 hours using supercomputer, while the ELS took only 3.5 hours using 6 processor the computer. So this gives you an idea about uh, how accurate and fast is the analysis if you are using the applied element method. We also did a case where we wrapped the core of the building with FRP just to see if this building is going to not to be damaged due to the earthquake if we do so. And we applied the earthquake again. And although there was like very big deformations, but the building was able to withstand the earthquake. Another example in here for what we called Margarita Palace. This building was actually damaged due to an earthquake, or there was like major cracks in this building due to an earthquake. So we used laser scanning to be able to detect the locations of the cracking inside the building. And then we created an ELS model for the same building with the cracking before or with the cracking modeled inside ELS. So the ELS has the ability to model also a cracked section from the beginning. Um, and then we did another earthquake on the cracked building, and we see that a lot of areas in here collapsed due to the earthquake. Another example in here also is for a stone tower. And in here, what we did is that we took also, or we used laser scanning to be able to model the rubbles and the mortar in between the rubbles of the stones that we see in here. So this is the meshing that we used inside. And then we applied an earthquake on the building. We see here the analysis results showing crushing and splitting and then failure. For the wind analysis, this is a very simple case for a car shed, and we applied wind load on it. Another example in here is for the corrosion effect or the ability to do analysis on a section that has like a corroded reinforcement rebars or areas of the concrete that are no longer exist. So in this example, we have 3 cases that we are going to show. The first case is for a pre-stressed concrete beam. We see here the pre-stressing cable inside. And as a verification, we are just going to apply a 3-point load on this beam, and we are going to see its the analysis of it. So from the point 1 to point 2, the beam is deflecting upward due to the pre-stressing. And then we begin loading the beam. and we will find that the failure here happened at around 62 kip. Now we are going to repeat the same example again after applying corrosion on the pre-stressed cable. And this will be done through the analysis, not from the beginning of the analysis. So at a certain time, we will give the information for the ELS to reduce the area of the pre-stressing springs inside by at certain steps like 100 increments or something, and we will see the effect. So from the point 3 here, we applied the weakening in the pre-stressing. So you will see that the deflection increased a little bit due to the reduction in the area. And then we begin loading the beam again. And we will see that the capacity of the beam has been reduced to 52 kip. We will repeat the analysis for the third time when at the point of the failure after the corrosion has been applied, we will add an FRP plate at this location. Just skip here a few frames. So we begin loading now. And remember that the failure had happened at around 52 kip. We added here the FRP plate, and we'll see that the capacity has increased to be 80 kip. So this gives you an option for the retrofitting techniques and the strengthening of buildings due to corrosion and so on. Impact analysis, we have also this case for a reinforced concrete slab impacted with a projectile. The projectile has a mass of 160 grams, and it is going through the slab with this velocity 165 meter per second. This is the ELS model, and in this case, we modeled the reinforcement rebars as elements instead of as the springs. And this is a comparison between the test results, hand calculations, and the ELS. We see here that the test said that the projectile is going to go through the whole thickness, but it's not going to perforate from the other side of the slab. And the damage region at the back is 170 by 190. Here in this area or in the hand calculation showed that the impact or the projectile is going to go only 30 millimeter through the thickness, not the whole thickness. And of course, you cannot get the damage region at the back. And the less we see here that the failure or the penetration was exactly same as the experiment, and also the damage region was very similar to what we see in here. Let's see here a video for the analysis. We see here it's impacting. This is the displacement of the projectile, and this is the velocity of the projectile with the time. Another example in here, or the same example, we are just showing the back failure, the um, the scapped region at the back, and we see here that although there is a very big damage area, but the reinforcement rebars did not fail. And this is what we got here also from the ELS, that the reinforcement rebars did not fail. Another example for an impact is this projectile impacting this steel plate is like having a mass of around 300 kilograms, and it is traveling with a speed of 100 meter per second. And this was actually a project that we have been working on, and they needed to know what is the minimum thickness that they can use for the roof of the building so that this projectile does not perforate from the slab. So we have done some calculations using ELS, and we see here that uh, with with a thickness of a plate 1.5 inch, we could be able to keep the projectile inside without perforating. Another example here is for the fire. We have here a reinforced the concrete beam subjected to an impact from this object, and once they are going to do it with an impact without heating, and then they are going to repeat the example again while the beam is inserted in an electric furnace. So let's see the results that we've got here. This is the hammer impacting the beam. I'm just going to skip few frames in here because this is very long. So it impacted, but it did not fail. And this is a comparison between the experimental results and the ELS results in terms of the maximum deflection of the beam. Now, I'm sorry. Again. Now they are going to repeat the same analysis again after inserting the beam into an electric furnace. Where we see here the impact, and we raise the temperature of the springs to a certain value, and we see here failure happening in the beam. And again, this is a comparison between ELS and the experimental results. Another example in here for a portal frame with RBS connections. And in here, we have increased the temperature of this column to around 1,000 degrees. And we see here the failure and the buckling that's happening in the column and the failure at the RBS connections. This is also an experiment that was done in the lab for a 4-point loading for a beam while it is under a fire loading underneath. And we see here the lateral torsional buckling that's happened in the beam. And this is a comparison between the ELS and the experimental results. Finally, the demolition analysis. So we have been consultants for many demolition contractors worldwide. In this example, this is one of the examples. So these are two stacks. One of them is 800 feet. The other one is 600 feet. And it was required that we submit how these stacks are going to behave during the demolition. So we did the analysis for this, and we see here the analysis of the ELS. And in few seconds, we will be able to see a comparison between the behavior of the ELS versus the behavior of the stack. We see here that the top part has been separated inside ELS, and this is the exact same thing that happened in the stack. Also, the other one was like two stacks inside each other, and we see the contact that happened in between them while it is falling. So I think we have reached now to the end of our presentation. If there are any questions, I will be happy to answer them.